Okay, so chapter 2 is about the study of motion. In humans, the efficient use of the body and the study of motion is called kinesiology. So we'll need to learn some concepts in motion in physics. Okay, so we'll keep it simple. We'll study motion in a straight line. Okay, so here's an example: a car moving on a straight road. Okay, and we will be interested in describing such motions and be able to calculate some of the stuffs. Okay, so in physics, the study of motion is called kinematics. Dynamics is the study that involves forces. Forces cause change in motion. That is, forces give objects acceleration. Okay, so that subject is called dynamics. Just the description of motion is called kinematics. So when to describe a motion that an object undergoes, okay, what you want to do is you want to give its position with reference to a coordinate system. So here's the origin. You want to give its position at all times. And that's what this graph is doing. So here's the x, that's the position of the object as a function of time. So what this graph is telling you is at 0 seconds, the car was at 30 meters. At 10 seconds, the car was at 50 meters. At 20 seconds, again, it's roughly at 38 meters. Okay. At 30 seconds, it's at 0 meters, and so on. Okay, so there's the position of the car at all times, and that's a complete description of this motion. Okay. And from this graph, you can calculate all kinds of things. So for instance, if you wanted to know the velocity of the car at this instant, all you do is draw a tangent line, and the slope of the tangent line is the velocity at that time. Okay. So this graph of position versus time is a complete description of the motion. Now in physics, there are quantities that are described by vectors, and then there are quantities that are described by scalars. Vectors are quantities that have magnitude and direction, and as the name suggests, they're represented by directed line segments. The length of the arrow tells you the magnitude, and the direction of the arrow tells you the direction of the quantity. So for instance, if an object is moving east at 10 meters per second, that would be its velocity, 10 meters per second. And if it's moving west at 5 meters per second, that would be its velocity. Okay. And in one dimension, you can choose to represent the direction with the sign. So right velocity is going to the right would be positive, and velocity is going to the left would be negative. Okay. Anyway, vectors are quantities that have magnitude and direction to them. And these examples of quantities that are represented by vectors are velocity, acceleration, displacement, force, and so on. Scalars are quantities that just have magnitude. They have only magnitude. Okay, and all you need is one number to represent them. Okay, so examples are speed, pressure, and so on. We will be talking about pressure quite a bit in biology. Okay, so quantities in physics are represented by vectors and scalars. The position is the location of a particle or the object that is moving. So for instance, here is this armadillo. He's moving along a straight line, and his position as a function of time is given by this graph. So again, On this vertical axis is his x position, and on the horizontal axis is the time. So for instance, at 0 seconds, he was at -5 meters with reference to this axis. At 1 second, he was at -4 meters. At 2 seconds, he was roughly at -2 meters. At 3 seconds, he was there. So again, here's a complete description of his motion, his position as a function of time. Now, a more useful form would be mathematically a motion of an object can be described by giving the position as a function of time. So give the position as a function of time. If you give a function like this is more useful. Let's say here's a motion, okay? And then you can calculate all kinds of stuff from it. We define a quantity called displacement. A displacement is, okay, so if you were here and let's say you went for a walk, this is in 2-dimension and you ended up here, your displacement vector is from the initial point to the final point, is a vector that points that way. So for instance, in this example, this person walked from here to there, and that's the displacement. You walk from here to there, that's the displacement. You walk from here in 1 dimension, you walk from here to there, this is the displacement, okay? So the displacement is a vector pointing from the initial point to your final point. So if you went for a walk from, started here, go there and come back, your displacement vector for this journey is 0, the 0 vector. So let's say you walk from here to there and then back there. In that case, the displacement vector would be this vector. All right, so the displacement vector is your final position minus your initial position vector. Distance, on the other hand, is the total distance traveled. So for instance, if you went for this walk, this was the displacement was this vector. And this distance is, let's see, what is it, 1 kilometer. So this is minus 0.75 kilometers. The negative sign just telling you that the displacement vector is pointing to the left. The 0.75 kilometer telling you the magnitude of that vector. Distance, on the other hand, is the distance you traveled, and in this case, the distance you traveled is 2.75 kilometers. So, displacement is a vector, distance is a scalar. Okay, so for this journey, that was the displacement, and this is the distance traveled. Average velocity for a person is, for an object in motion, is average velocity is the displacement divided by the time over which that displacement happened. Okay, so that's average velocity. This quantity is measured in meters. This is in seconds. So units for velocity would be meters per second. So for instance, let's say you started off here, went to New York and came back home. Your displacement is 0, so yeah, and it might have taken you 2 days, but the 0 vector divided by 2 days is your average velocity would be 0. Average speed is the distance traveled. So in this case, the distance traveled is 2.75 meters. Divide the distance traveled divided by the time over which that distance was covered. All right. Now here's the thing about average velocities and speeds. Neither average velocity or speed provide details of the trip. All right. And actually, so for instance, you went to New York and came back, your average velocity is 0, your average speed is not 0. Of course, it's the distance covered divided by the time, so average speed is not 0. So average velocity and average speed are not related. Acceleration, when your velocity changes, you're accelerating. Okay, anytime your velocity changes. And acceleration is defined as the change in velocity divided by the time over which that change happened. So if a certain amount, your velocity changes by a certain amount, and that happens in a short interval of time, then your acceleration is high. All right, so here's something that you encounter, the relationship between velocity and acceleration. So here's a car traveling its constant velocity, and that's indicated by the arrow is pointing in the same direction and the magnitude of the arrow is not changing. Here's a car that is speeding up. The velocity and acceleration are pointing in the same direction, and so the velocity is increasing. So this is what happens when you accelerate, and this is what happens when you brake. So here's the velocity and your acceleration is in the opposite direction. Okay, so when the acceleration is in the opposite direction, you see the magnitude of the velocity is decreasing. So you're slowing down. All right, no acceleration, velocity is constant. Acceleration is pointing in the same direction as the velocity, you're speeding up. Acceleration pointing in the opposite direction of the velocity, you're slowing down. Okay, so we'll see a couple of formulas of motion with constant acceleration. When the acceleration is constant, okay? So you see, that's what this graph shows you. The acceleration is constant with respect to time. Acceleration is constant. When acceleration is constant, the velocity increases linearly with time, and the position increases quadratically with time. Yeah. All right, so when acceleration is constant, and this is one-dimensional motion, that is motion along a straight line, what this gives you is, for instance, this gives you how your velocity after time t. So this is giving you velocity as a function of time. This is giving you a position as a function of time. Okay, so x naught is your initial position, x is your final position. So that's the displacement. This is giving you your position as a function of time, and again, average velocity times time. And average velocity is final velocity plus initial velocity divided by 2 times time. And here's another equation. This is giving you final velocity square as a function of your displacement. Your final velocity as a function of how far you've traveled. All right, so we will use these formulae in simple problems, and these formulae are valid when acceleration is constant. Okay, so for constant acceleration. Now here are the motion where you do see constant acceleration. Constant acceleration is really very, you don't experience that for too long in real life. Okay. So you might experience constant acceleration for 2 or 3 seconds. But here's an example where you can experience constant acceleration. A freely falling object experiences constant acceleration due to gravity. Okay, and if air resistance is negligible, acceleration due to gravity is denoted by g, and the magnitude is 9.8 meters per second square, and it's pointing downward. That's the direction in which the acceleration is. So for instance, if you toss a ball up with an initial velocity, since the acceleration is pointing downwards, it'll slow down. The ball will slow down. So its velocity will decrease, eventually go to 0, and then it'll turn around and the velocity will start increasing. Okay. So in this direction. So the acceleration due to gravity is pointing downward, and the magnitude of the acceleration is 9.8 meters per second squared. All right, so we'll go over a couple of simple problems here that you need to be familiar with. Okay, on the test there's similar problems, so you just have to follow this procedure. Okay, so what this problem says is a sprinter is able to produce an acceleration of 8 meters per second square for the first 0.75 seconds of a race. Calculate the velocity of the sprinter at 0.75 seconds. So here is the equation you'll use. Final velocity is initial velocity plus acceleration times time. Okay. So if you start off from rest, this is 0. Your acceleration was 8 meters per second square. And after 0.75 seconds, your velocity will be that times that, one of the seconds cancels. Okay. So, and 8 times 0.75 is 6 meters per second. So if the sprinter starts off from rest, has an acceleration of 8 meters per second square, after 0.75 seconds, she'll be moving at 6 meters per second. All right, so look at those problems closely. In this problem, you're calculating the displacement. There's the initial velocity, and there's 1/2 acceleration times t squared. Okay, so the initial velocity is 30 meters per second. There's 30 meters per second. You're calculating the displacement after 2 seconds. T would be 2 seconds, and acceleration is 9.8 meters per second squared. That's the magnitude. So in this problem, a tennis ball is hit straight up with an initial speed of 30 meters per second. So initial speed of 30 meters per second. So if you choose that, since we've written this as positive, we've chosen that to be positive direction, and the acceleration, which is pointing in the opposite direction, will be minus 9.8 meters per second squared. Okay. So in this problem, so the displacement is initial velocity is 30 meters per second, and you're traveling for 2 seconds, plus 1/2, there's the negative acceleration, plus 2 seconds squared. Okay, so the displacement is 40.4 meters. So the tennis ball will be 40.4 meters up after 2 seconds. That's what this is saying. And in this problem, in this part, you're calculating the final velocity. Final velocity is initial velocity plus acceleration times time. Again, initial velocity, that after 2 seconds. Okay, so there's the initial velocity, v naught. Acceleration is negative 9.8 meters per second square. That's because, again, the initial velocity was that, pointing in that direction, and the acceleration is in the opposite direction, 9.8 meters per second square. Okay. All right, so the final velocity is initial velocity plus acceleration times time. 30 meters per second minus 9.8 meters per second squared times 2. So the final velocity is 10.4 meters per second. So after 2 seconds, the ball is still rising up, except that the velocity is 10.4 meters per second. Okay, so that's what the solution is. All right, so that's a brief lecture on chapter 2. Study the slides well, and good luck on the exam.